Just of time, I'm going to get started. So I hope you all had a good lunch. And so this afternoon, we're going to cover more advanced topics. So mainly, we're going to cover, do I have the schedule? Yeah. Well, mainly, we're going to cover model selection, so setting hyperparameters, deciding if your model works well or not, deciding how you can improve your model. We're going to go a bit more in depth with a few specific estimators just to get you to know them better. And then we're going to move a bit towards working on bigger data sets because big data is very popular right now. All right, so I'm going to get started with how to set parameters to validate a model and to test it. And so this is, I hope you all have the notebook. This is notebook 6.1. All right, so I'm going to just do the standard imports and switch by that to inline mode. And then first, a bit of discussion. So we've already mentioned this morning what overfitting was. So overfitting is basically when you're trying to learn a model that is too complex for what your data supports. So, I mean, a typical example is if I give you 2 data points and I'll ask you to learn a plane in 3D. Well, quite clearly, you cannot do this. There is an infinite number of planes that will go through 2 data points in 3D. Now, that might not sound like a problem. You say, well, just pick any. But what if my data has noise? So you're learning a model that's too complex for what your data supports, and if you do this, you're capturing the noise. So it might be interest to backtrack a bit and learn a model that is simpler. That's called overfitting, and the converse is underfitting. When you're learning a model that is simpler than what your data supports, then you probably should crank up your model complexity. And controlling for overfitting is the general notion of regularization that I already mentioned this morning. So what we're going to try to figure out is, are we overfitting or underfitting given a data set? How can we tune a parameter of the model to have the perfect sweet spot? And I'm going to start with a very simple example just to give you intuitions. So I'm going to take a data set with only 2 data points. So I've got a 2D X array that has 0.5 and 1 as observations, and I've got Y equals 0.5 and 1. Why do I have X test in there? Right, and I'm just going to fit a simple linear regression model to this and plot it. And it is not going to work because it's working. Where is X test defined? Oh, it's defined there. Okay, excellent. Okay, so I get a bunch of warnings because there are things being added to sys.path, and then I've got this. Okay, so this is like the simplest example you can think of. I've got 2 data points, I'm fitting a line into this. Works fine. Okay? Well, what if we have noise? So what I've done here is I've added a bit of noise, wiggling on X, and fitted the line. So what we can see is because so I'm fitting 2 things here, right? I'm fitting an intercept and a coefficient. So I'm fitting as many parameters as I have a model, a data point. And what we can see is that if I add a bit of noise, my model is all over the place. It fluctuates completely with my data set. Intuitively, we can say that it's amplifying the noise in the data. And if you're a statistician, you say, well, it has a lot of variance. And so we can use another estimator that's a linear model that works really, really close to the linear regression, which is an ordinary least square, which we call a ridge. And what this model does is it systematically biases the coefficients to be closer to 0, under the assumption that, if I take random observations out in the wild, well, they're not going to be correlated. The coefficient should be 0. So if we do this, I'm going to just rerun the same simulation with the same noise model. I'm setting the seed with the ridge. And the parameter alpha of the ridge controls how much bias I have. I'm just running this. What can we see? Well, we can see that the model is systematically biased. It's below the line that would go through our data points. But it's got much less variance. So we see that we're biased with less variance. And that's a fairly common trade-off in statistics. So no bias will often give you a lot of variance. More bias will reduce the variance. And the question is to choose the sweet spot to get a model that is biased, but with little variance, and then leads to good decision rules. Okay? So I see a lot of people thinking of bias in statistics as a bad thing. Well, if you have noise and a small number of data points, maybe bias is a good thing. You just have to choose your bias well. So that's regularization. All right? So the question is, how do we choose the trade-off between bias and variance? And Jake is going to cover this with learning curves.
Okay, so as Gaël said, the bias variance trade-off is one of the most important aspects of choosing a good model for your data. And so a way that you can address this is through this process of creating what we call learning curves or validation curves. So I'm just going to load in a quick function that we have in our helper functions to plot this curve right here, just as an illustration. And this is another illustration of the kind of thing that Gaël was talking about. Here what we're doing is we have a set of points that are drawn from a particular model, and we're trying to fit them with a polynomial fit. So on the left we see if we set the polynomial degree to 1, we basically have a best fit line. And you can see that it does not fit the data very well. The model's not complicated enough to fit that data. On the far right, we have the converse. So we have a d equals 6, a 6th degree polynomial. And we see that the line fits the data basically perfectly. It goes through every single point, right? So we have a perfect model, right? But if we were to draw some other points from that distribution, it's very unlikely that the model would go straight through those points, right? Or that the model would be even near those points. And in the middle, we have kind of the middle ground. We have a d equals 2 polynomial, which seems to do a better job than either of the extremes of fitting the data. So when we talk about bias and variance, and we talk about underfitting and overfitting, this is the image that I want you to have in your mind, that we have these points. Underfitting means we're trying to fit a line to a point or to a set of points that can't be fit by a line. And this is a high bias model. A high bias model is one that no matter how much you adjust the parameters is not going to give a good fit because it just simply isn't good enough to explain the data. It's a biased model. On the far right, it's an overfit, which means that it fits the training data perfectly, but it won't generalize to new data very well. And we call that a high variance model. And the reason it's called a high variance model is if you were to perturb those points a little bit, the model itself would change a lot. So for example here, if we replot this instead of using random seed equals 42, which is the best number to use, if we instead use random seed equals 2, you can see that the underfit and the medium model didn't change very much, but the high variance model changed a lot, right? And if we do that again, you can see that again. Whoops. So the high variance model really depends on exactly which data you put in, while the other ones don't really depend on the exact data set that goes into it. So that's where the high variance term comes from. So like Gaël said, we're trying to find models that are in the sweet spot between this bias and this variance trade-off. So one way to look at that is to do validation curves. So here we're going to basically plot as a function of the degree of the model. We're going to plot the training error and the testing error. So we have this test func. This is basically it has this function 10 minus 1 over x plus 0.1. That gives us the underlying true value. And then we add some sort of error to it, normalized error. And then we can compute the error using this value right here. You know, we could also use from sklearn.metrics import mean squared error or something, but we're just doing it by hand in this case. And as before, in the previous section, if you were here, we'll use the train test split to split our data set into a training set and a testing set. We're going to randomly sample some data, split it up, and then scatter the train and the test so we can see that. What did I do wrong? Oh, always execute your cells, Jake. There we go. So this is the data that we're looking at, and the training data is red, the testing data is blue, so we can kind of see that it's drawn from the same distribution. Now what we'll do here is we're going to use degrees between 1 and 20. These are the polynomial degrees, so 1 is fitting a line, 20 is fitting a bunch of curves through the data. We're going to go through these and use the polyfit function. So this is, we probably should have used the linear regression here. It does the same thing, but it's just, this is a more basic function to do the same sort of fitting. We'll get the train error by computing the error on the training set itself, and we'll get the validation error by computing the error on the test set. And then we'll plot the results. So let's take a look at what we see here. So this is a fairly typical validation curve. And I'm going to zoom this all the way in so we can take a look at it. And what we see is that when the degree of fit is low, say when we're underfitting, when we fit a line to a data that can't be described by line, to data that can't be described by a line, what we see is that both the training error and the cross-validation error are very high. So high training and cross-validation error are indicative of a model that's underfitting. It's a biased model. And as we go out to the other side, we see that the training error becomes very low, and the cross-validation error starts to increase just slightly. If let's change the y limit here to 0, 1.8 or something like that. Where did it go? Oh, yeah. So we can see a little better that the cross-validation error kind of hits a minimum and then is tending upwards slightly. So when you have a very low training error, like we see out on the right side, very low training error and a higher validation error, that's indicative of a model that's overfitting the data, right? It's a model that's does very well on the training error because it has enough on the training set because it has enough degrees of freedom to basically fit all the points, but it's fitting those points too well and it can't generalize to a new data set. You guys see that? This might be a little bit abstract here, but this is an important point that we have underfitting on the left-hand side and overfitting on the right-hand side. Yeah.
Does that small spike tell us anything? Or is that
yeah, that small spike is just basically noise. It's probably due to just the random sampling, the random split of the data. Yeah. Yeah, so he mentioned that if you turn up the degree of the polynomial to, how far did you do it? 50 or something? 200. Yeah, if you turn the degree of the polynomial up very high, you'll start seeing some very weird, noisy behavior. And that's mainly because the problem is becoming ill-posed at that point, because you're trying to fit too many parameters to too few observations.
the polyfit algorithm also doesn't work from full order. You can't factorize the polynomial. You lose precision.
Oh, okay. So he mentioned that the polyfit algorithm we're using here actually doesn't work at that high of orders. Yeah.
I'm curious, in the earlier simple example we plotted just the three different
Mm-hmm.
plots, I would naively look at those and say that the in the degree 6 overfit than it was in the other fit.
Yeah.
Whereas here, you've got just this very shallow rise. You've got a much higher order polynomial, which, I mean, I see what you're saying about there being a minimum there and sort of an optimal place to be, but it doesn't look like it gets dramatically worse for going to very high order polynomial.
Yeah, because part of that, part of it is because we have many more points here. If I were to change this, say, to 50 points, actually, we should probably do 100. 50 will be too few. Then we're going to see where'd it go. No, maybe I should have done 100 or 50. So the reason the error got really bad there, so here we see it, because essentially when we're looking at the polynomial of degree 20, it can fit 20 points perfectly. And so when it tries to fit those 20 points perfectly, it'll just be swinging wildly all over the place.
But with many more sets of points in the data set, you're not going to get those wild oscillations.
Right, right. Yeah. So this is pretty typical here, and maybe this shows it a little bit better, that when you want to choose the optimal model, you're going to choose the optimal model based on where the test data finds its minimum error. And if you try to search for where the training data finds its minimum error, you're just going to go off all the way out to left field where the model fits the data perfectly, and then your test error is going to be way blown up, right? So this is the validation curve aspect when we're choosing the complexity of the particular estimator. Now there's another question that goes into this, which is the next part we're going to look at, which is, so say you have a given estimator that is giving you a particular performance on your test set, and you want to improve that performance. There are several things that you could do in this case. You could think about adding more training points, right? You could increase the size of your training set, and that might affect things. You could add more training features. You could go out and observe more things, or ask people on the surveys more questions in order to fit the results. Or say if you're doing text classification, you could go from 2 grams to 3 grams to 4 grams and get all combinations of features. You could do things like add regularization, like Gaël was talking about, basically force the model parameters to underfit or to overfit the data more. And this is a real question. When you have your model that is not doing well enough on your data, how do you make it better? And it's a question with real consequences, right? Because, so for example, in my field in astronomy, let's say we're trying to measure the redshifts of galaxies, and we're not doing well enough to measure the cosmological parameters we're interested in. Do we spend our telescope time observing more galaxies and getting a bigger training set? Or do we spend our telescope time observing the same galaxies again through different filters and getting more features? And that's a real question we have to answer. You know, we have to decide these telescopes cost millions of dollars to build, and we want to use them effectively. So it's not just a theoretical question. And these learning curves are something that can help you answer that question in your own particular situation. So what I'm going to do here, there's a typo here. If you see where it says random state equals j, I want to change that to random state equals I. This is just making sure all the random states are initialized in the right place. What we're going to do here is plot learning curves. And what a learning curve is plotting the training and testing error as a function of the number of samples, the number of training samples. So let's look at this function and see how this does it. We want to plot the learning curve for a particular choice of d, the polynomial fit d, and we're going to have the maximum number. So we're going to do sizes that range from 2 all the way up to that maximum number. And then we're going to make a training error and validation error array here. And we want to do multiple runs because multiple runs allow us to beat down some of that variance and the weird spikes that we saw in the earlier example. But we're going to go through all the different sizes from 2 to 200. we're going to do a train test split and get out the correct number of points here. We're going to run our polyfit, basically run our machine learning model. And then we're going to compute the validation error on the test set and compute the training error on the training set. And then finally, we'll take the mean over all those different random samples that we did, and we'll plot the results. So this is just a utility function to plot learning curves. Currently, there's no built-in utility in Scikit-Learn to do these learning curves, but that's something that we're hoping to address in the near future because they're a useful thing to do. So I want you to think about this real quick right now before pressing enter on the next cell. So as the number of training samples are increased, what do you think will happen to the training error and the testing error? So think about that. We have a particular model. Say we're fitting a d equals 3 polynomial. And as we add more and more training samples, what will happen to the training error? Yeah, that's right. They'll get closer together. But which one, will the training error be going up or be going down as we increase the number of samples? I hear people, anyone have a logic for why they think, who said up over there? Someone, yeah.
Because if you have more points, then with a 20 order probability, you can't really fit it perfectly. So
Yeah.
with the same order, just if you increase the training set, you're going to increase the error.
Yeah, that's a good point. So he said that if you increase the size of the training set, you can't fit it perfectly anymore, right? So as a quick example, if you have 3 points and you're doing a degree 3 polynomial, you can go through all of them. It's pretty easy, right? But if you have 100 points with a degree 3 polynomial, you're not going to be able to hit all those points. You're going to miss some of them. So the training error is going to go up as we increase the number of samples. What about the test error? Yeah.
I'm guessing that the test error goes down because at this point your test distribution should be more similar to your training distribution because there's something like that.
Right, yeah, so that's good. She said that the test error, she expects the test error to go down because as you increase the number of training samples, it's getting closer and closer to the test sample, right? As long as they're split evenly. So essentially what we expect then based on this is that we'll have a plot like this where this is number of samples and this is the error. And our training error for a low number of samples will be 0, right? Because we can fit it perfectly, but it'll be going up. And our test error, when we're high bias, or when we have a very low number of samples, our test error will be high and then it'll start going down. Another question, do you guys think these two, the training error and test error, will ever cross? Will you ever be able to fit the test set better than the training set? Anybody have an idea? Yeah, so if not for reasonable, kind of on average, you'll never do better on the test set than on the training set. But you might have kind of a lucky draw, or you could imagine engineering a situation where that would happen. But in general, you'd expect the test error and the training error to kind of never cross and to sort of approach some equilibrium value, right? So this is the kind of thing, this is what we call a learning curve. And I drew kind of the schematic version here, and now we're going to see that in real life it's not always quite as neat. But we see that same sort of thing. So here's the learning curve. If we plot the learning curve for d equals 1. And again, remember to change this j to an I here. That was a typo that we had in our notebook, and we'll fix that later. So for d equals 1, what we see is that, as expected, the validation error, the test error, starts high. The training error starts near 0. And they increase, and they come together, and they meet somewhere in the middle. Now, we saw before that the d equals 1 model here underfits the data. It's a high bias model. And one way you can read that off the graph, the fact that it's underfitting the data, is that as the training set size grows, they've basically converged to the same value, right? This model doesn't have enough complexity to fully describe the training data. So in this case, what we find is that we've basically converged on a particular value. And if we were to add more training sets, we could add millions of more training sets, right? And this would pretty much have the same performance. So when you have a biased model like this, the d equals 1, we're fitting a line to tons of points. The line will never describe those points. Adding more training samples is not going to help. So in this case, when we've seen these converge, when the training error and the test error is very close, it's a high bias model, like I said, and there are a few ways that we can improve this is by, one, using a more sophisticated model. So in this case, we could increase D, we increase the complexity of the model, add more polynomial features to it. Another way to increase the complexity of the model is to gather more features for each sample. So we basically have more degrees of freedom to fit. And another way, if we're using a regularized model, we could decrease the regularization. This is the thing that Gaël talked about a few minutes ago when he was, the regularization is, as you increase the regularization parameter, it adds bias to the model. It kind of biases you towards what you would expect it to be. So a high bias model is, once again, when you see that these things have converged, training error is near the test error, then you can do any of these things to kind of make it a little better, to try to improve your results. So any questions there on the high bias model before we move to the high variance model? Yeah.
My curve keeps seeing the asymptote to the same point, and I'm looking around, it looks like some other people do.
Yeah, there's a random seed in here that wasn't set, so some of the particular results will be different, but you should see, in either case, you should see them kind of converging and coming near each other, if not touching each other. Yeah? Oh, Olivier has a comment.
Okay. Sometimes they don't merge because you can have a model that is both biased but still overfitting, so still underfitting and overfitting at the same time, because the kind of bias that you put is not able to reduce the variance. It really depends on the task. So for instance, here we are regularizing by decreasing the degrees, but we could regularize by penalizing the coefficient of the polynomial, and it might be a better way to regularize and reach a better trade-off.
Okay.
But I don't know why it's different on your machine than this.
Yeah.
Set your seeds, people.
I should set my seeds too. That's true. Yeah, other questions right now?
Well, I mean, is this also telling us, the minimum size of the training set that we need to get a reasonable model?
That's true. Well, it's telling us, so the question was, is this also telling us the minimum size for a reasonable model? What this is telling us is the minimum size for a reasonable d equals 1 model. So if you what it's saying is that below, say, 20 points or something like that, a d equals 1 model is probably doing pretty well, and you might not be able to do much better. But higher than 20 points, you see more of those, more aspects of the training set. So it's kind of all together. So this, we'll see this a little better if we actually plot a high variance model. So with d equals 20, whoa, I don't want my y-lim there. What if I change that? Ooh, I probably want my y-lim there. This is why you should set your random seed. Listen to Gaël. So I'm going to set that to 30. Yeah. Wow. This worked way better with my initial random seed. I don't know why it changed.
That second plot somehow like
So I think part of what was tripping me up here is that I changed from 200 to 50 previously, 200 points to 50 points. So I'm going to change it back to 200 points and see what comes there. Actually, I don't know if that affected things. So there's my d equals 1 that's converging like you had. And now let's try our d equals 20. That looks a little better. So we're seeing that for the lower amounts of noise, or lower amounts of degrees, we're seeing a little bit of noise. But generally, what we're seeing is that again, the validation error is tending down with the training size. The training error is tending up with the training size. And at this point, we can tell that we have a highly variant model. We have a model that's overfitting the data. That's because even for 100 points in the training set, we have training error and test error that are very far apart, right? So the model has enough degrees of freedom to basically perfectly fit, well, not quite perfectly, but almost perfectly fit the training data. But when it's perfectly fitting that, it's not doing a good job of generalizing. So these are the two extremes that I want you to have in mind. This is overfitting the data. Adding more samples is not going to help you here. You need to improve your model. And underfitting the data here. Sorry? Oh, my bad. Yeah, this is underfitting. Underfitting the data, adding more samples is not going to help you. And here is overfitting the data. And at this point, you can see that adding more samples when you're overfitting is a good strategy, right? If you're stuck with this model, then you could add maybe out to 1,000 samples, and that training error might get down. And eventually, if you add enough samples, then this model would be pretty good. So again, looking at what you can do in this case, when you have an estimator that's overfitting the data, you can gather more training samples, like I said. You can somehow use a less sophisticated model. So in this case, that would be making D smaller. Or kind of equivalently, you could increase the regularization. So if you penalize those polynomial terms, like in Gaël's example earlier, then you're able to impose some bias in the model. And in this case, the bias helps you. It helps get you away from that overfitting situation. So questions there? Yeah?
So what are some other methods of regularization besides punishing?
Other methods of regularization? Basically, regularization is punishing higher order terms, unless you guys have some more input on that.
Okay. It depends on the model structure. For polynomial models, you can reduce the weight of the coefficients or the number of monoms. But for a linear model, it could be the weight of the dot product. For decision trees, it can be the depth of the tree. It really depends on the model. For instance, for kernel support vector machines, you could put a constraint on the number of support vectors. That's another way to regularize. It's not very common to do it this way, but it could be a way.
And sometimes the border between regularization and changing the model is kind of fuzzy, because, like Olivier said, you can set the max depth of decision trees, and in some senses that's a regularization, but in other senses that's fitting a different model. So it kind of blends together. Yeah. Mm-hmm.
You said that if to improve the model, you would reduce the value of D.
Mm-hmm.
So I reduced it to 10, and I looked at the graph, and I hope I have the correct interpretation, but it tells me that the optimal training set size would be like 50. And beyond that, you're not really gaining anything.
Yeah. So in this situation, when D equals 10, when you add more training points than say 60, you're not getting much more information from that. Sounds like these guys have Yeah.
Yes, in this case, the data set is noisy, so you can never reach perfect accuracy because we added noise in the data set voluntarily. And you can see the dashed line here is the theoretical, the best model that we can fit. So we can actually reach it quite quickly in this case.
That said, I mean, your question really depends on your measurement of error. Here we're looking at mean square error. If you're looking at the graphs with your naked eyes, you may say, well, I think my graph is, my plot is still wiggly. I don't like it. That's because you might have in mind an idea of also the derivative. You don't like the fact that it's got high derivative. You'd like only low derivatives, in which case you want to basically change your measurement of error. Does that make sense?
Yes. Yes.
Mm-hmm.
Yeah, just in continuation of what Gaël just said, I can enforce any error measurement that I think makes sense in terms of my data taking, right?
Right. You can choose whatever metric you want, and if you look, so I did an exercise on that in my Scikit-Learn tutorial last year here, where essentially we were looking at some astronomy data and first looked at it in terms of one error metric, which was mean squared error, and then looked at it in terms of another metric, which was the percent of outliers beyond a particular error. And in different cases, you might be interested in different metrics.
Sorry. So you can use different metric to quantify the error of the model, but sometimes the model will not optimize this specific metric. So you have to be aware that the model has a proxy on the loss that you're trying to solve. And sometimes it's a simpler version, a differentiable version of your ideal measurement to make it better, easier to optimize.
Yeah, so instead of going to degrees of polynomials, could I go here with a Jacobi matrix and try to make different differentials and see if that improves actually my kind of model?
Yeah, the question was, can you use something like a Jacobian matrix and look at different models? And I think, yeah, you can. If you can write a model, you can write a loss function and you can optimize it.
Yeah, so this is getting a bit outside this tutorial, but yeah, this is basically statistical learning theory. If you know it, I mean, depending on what part of statistical learning theory, you might write a Bayes learner, a learner that minimizes an empirical cost, and that's designing learners, which is, I mean, one thing I work on, but it is beyond this tutorial. Right, the learning curve idea still would work. What's important to keep in mind is that we're talking about two different things that are very related, which is your model space. So when you're talking, here we're talking polynomials, we could have linear by parts, and your regularization, which here is part of the model space, which is to say, well, I'm going to reduce the order of the polynomial, but could be saying, well, I'm going to bias to 0 the coefficients, and we're going to cover this more in details in the linear model section.
I have a question that's related to that, but I think closer to the tutorial. So at the very beginning, you talked about kind of trying to expose the bricks underlying Scikit-Learn, right? Mm-hmm. So does any of your methodology actually allow you to change the loss to some other differentiable loss, right?
It depends on the model whether you can change the loss. Some of them have things built in, like for example, if I from sklearn, sklearn. I want to do SVM import linear SVC. Then I can do linear SVC tab. Come on, there we go. So this you can set the penalty and you can set the loss explicitly. So in this case it's an L1 or L2, and I think there might be other options. Do you have something else?
Yeah, also there are online or stochastic gradient descent has a lot of different losses. But you can see that it's a closed set of options. And the reason is that the general framework here is an optimization framework. So if you really want to do this, you want to use an optimization toolkit like SciPy Optimize. You can be either generic or performant or neither, but you can probably not be both.
Yeah. Okay. Other questions right now? So I think I've summarized this pretty well already, but this is just what to do with high variance and high bias models, the strategies you might employ to improve your optimization. There's some more sophisticated methods for doing this cross-validation. Here we were kind of doing it by hand, right? We were going through 20 different splits and then computing the score. There's some tools in Scikit-Learn.cross-validation, that submodule, that do some of this automatically. There's k-fold cross-validation, there's shuffle split and things like this. And we'll cover a few of those a little bit later. And one last caution on this front before we move forward. The interesting thing about this, what we've been talking about is hyperparameter estimation, right? You have your model hyperparameters, and in this case, the hyperparameter was the d, the polynomial degree. So d equals 2, d equals 3. And what we're really doing when we do something like this is we're optimizing the hyperparameters for the test set, right? So just like you have to split the training set and the test set in order to fit your model, you can overfit the training set. You can also overfit the hyperparameters to the test set. So what it means is that it's often good practice to have not just two sets, but the training set, the validation set, and the test set. So what you'll end up doing is you fit your model to the training set, you fit your hyperparameters to the validation set, and then when you want to know how well you're going to do on brand new data that you haven't seen before, you test that against the test set. Did I say that correctly? So you fit your model to the training set, hyperparameters to the validation set, and then you get your estimated performance on the test set. Because there's these two levels of overfitting that can happen. Does that make sense? Yeah.
Do you guys have any thoughts on what I would call like a regime shift?
I don't know what you mean by that.
So I would say it might be like, say, a good area would be finance. You know, so you have some data that you're fitting, and it works well for a number of years, but then maybe something really changes with interest rates, or there's a new elected official, or a government changes. If you're going to analyze economic data, for example, what happened before and after the fall of the Soviet Union might give you very different information. But obviously, you don't know the future, right? So you're creating something that could have a very sharp regime shift.
Yeah, so for the people on the video, the question was about what if you have a regime shift, for example, if you have time series data modeling economics where after a while the economic situation changes and all of a sudden your models are wrong. That's kind of an online learning example, where you're trying to update your model with observed data at the same time as you're predicting what's going on. We don't have many specific tools for that in Scikit-Learn, but it would be along the lines of doing something like continuous cross-validation, where you're continually updating and testing your model as you go and seeing how well it's working with the most recent data. And Olivier might have some input.
As you said, we don't model online learning correctly in Scikit-Learn. We don't feature many models to tackle this particular problem. But most of the model and the methodology, like we presented here for cross-validation, they make the assumption that the data set is independent and identically distributed, ID. To test this assumption, what you can do if you are dealing with time series data is split your data into two training sets based on a time split, and then fit a binary classifier. And if your binary classifier is able to perform better than chance, better than 50%, it means that you have a shift and that you should retrain on the last data and forget about the two whole data.
Could you adjust the components if there's certain factors, right, and that factor is not present anymore in the regime shift, and you can just exclude it maybe? Or?
So the question is, could you adjust the components? And that's the stuff that you want your learning algorithm to do. So once you retrain, if you have a good enough model, it should pull that out for you.
Yeah, there's a whole body of research in this area that's in the online learning literature. You want to look at things like what's called the bandits, the multi-arm bandits. They're completely dedicated to these problems. They have things like memory and they forget, or they can detect regime shift. It's a complete literature that we're not covering in the Scikit-Learn. I don't think we'll be covering because it's fairly specific. It's fairly specific to an area that generates a lot of money, so it gets a lot of attention, but it's specific.
What is this called again? Multi-arm?
Multi-arm bandits. You got the one-arm bandit and the multi-arm.
Bandits.
Yeah, bandits.
Bandits, okay.
Like a slot machine.
Exactly like the slot machines.
So we're going to move on to Notebook 6.2 now, and this is just going using some of the principles from the last notebook and applying them here. So we'll use the inline mode. And we'll look at this diabetes data set. So this is another data set that's built into Scikit-Learn. And what it contains is, it contains some training data. It's 442 samples, 10 features. And those 10 features are kind of health indicators, people's age, people's weight, things like that. And the predicted values, or the 442 labels, are an indication of whether their diabetes improved or got better. So these are patients with diabetes, and what we want to be able to do is predict that see if we can predict based on what we know about a patient, what these measured medical attributes, if we can predict whether their illness is going to get worse or better. And so we'll be using ridge regression and lasso regression. So these are two regularized linear regression schemes. And what's nice here is that we'll be able to tweak the regularization parameter alpha in order to tune the model and try to do these sorts of learning curve things. So again, my Python install is not very happy right now, but we'll skip over that. So import those. And so this is just a very quick way to check the score of a particular model. So this is a score of 0 is bad, 1 is good. So we iterate through the two models. We instantiate it with its default parameters. We print its name, and then we print the cross-validation score of the model with X and Y. So this is just a very shorthand way of doing something similar to what we did before, which was split the data into pieces, train on one half the data, test on the other half, and then go back and split it into other pieces, train on one half, test on the other half. And it does this, in this case, I think 3 times and gives you back an average cross-validation score. So that's much better than writing this huge nested loop that we did before. So there are these nice tools to do these sorts of things. So what we see here is that the ridge regression with the default parameter does just a little bit better than the lasso with the default parameter. So right now, what I want you guys to do as a bit of an exercise is to do some basic hyperparameter optimization. So we have this way of computing the cross-validation score for X and Y. Now for this range in alphas, -3 to 1, write a loop over those alphas and compute the cross-validation score for each one. And we want to see for ridge and lasso, which is the optimal choice of alpha for this particular problem. So go ahead and take a few minutes to do that right now. And alphas is not defined because I didn't execute that. There we go. And we run it and we see this right here. So we see that both of them attain about an equal score, but it takes a very different level of regularization for each one in order to do that. And Lasso here is the L1 regularization, so it's penalizing the absolute size of the coefficients. And Ridge is L2 regularization, so it's penalizing the square of the coefficients. So you can see that if you dig into the code. Well, so this sort of thing is common task and nice to be able to do quickly. So there's actually this grid search module in here that does it automatically. So if we import from sklearn.gridsearch, gridsearch CV, we iterate through the models and we say, we train this. Gridsearch CV is a meta estimator, so it takes an estimator as an argument. And then we have a dictionary of the hyperparameters we'd like to test, and then the type of cross-validation. And when we click fit on a data set, then it will give us our best parameters. So you can see this finds just about the same results as the by hand version that we did up above. So it gives you the best options. And the cool thing with Grid Search CV is you can use it for any estimator in Scikit-Learn. I suppose you could even do a Grid Search CV of a Grid Search CV if you felt devious, but I don't know what that would give you. And then I should also mention that for some models, the cross-validation can be done more efficiently if you know that you're doing cross-validation from the beginning. So Ridge and Lasso are two of those. So they actually have specific estimators, the Ridge CV and the Lasso CV, that perform this grid search automatically. So we pass them, when we instantiate this model, we pass them the list of alphas that we want to do, and then we fit. And as part of that fit, it actually chooses the best alpha value. So that's something that there's several other estimators that's available for as well, if it's the case that it can be done very efficiently. So this is just a way to automatically do this type of hyperparameter estimation on your data set. And most of the dirty work, writing those nested for loops and all that, is taking place in the background. CV means cross-validation.
What does it do, that number 3?
Oh, this one right here? Oh, little CV, sorry. So what you can do, we can take a look at this if we want by, say, Lasso CV and look at the doc string. Actually, let's look at the full documentation. So we can see the CV here is either an integer or a cross-validation generator. So there are cross-validation objects that you can create if you want to specify the type of cross-validation to do. If you specify an integer, which is what we do here, let's see, it's the number of folds. So this uses a k-fold cross-validation with k equals 3, which means it's essentially breaking the data set into 3 parts and then training on 2/3 of it each time. Yeah. So there's more documentation. We're not going to go into detail on all the various cross-validation tools in here, but there's some detail online, and you can read through the docs and see that. But essentially, there's several cross-validation strategies that can work better in certain situations. Let's skip over this exercise and move on to the next thing. Is that all right with you guys? Yeah. Okay, so that's cross-validation, and that's model testing, some hyperparameter fitting, and again, we'll build on this as we go forward into some more complicated examples. But for now, we're going to switch gears a little bit, and what are we doing now? We're moving into going in depth into a couple different estimators that you might end up using. And so Gaël is going to come up and talk about SVM, support vector machines.
So now we want to cover a few estimators that we think are both useful for prediction problem and useful to get intuitions. And we're going to start with the support vector machines. The support vector machines are probably right now the estimators, the learners that are most used in machine learning settings in general. Of course, if I said this at a machine learning conference, there would be a huge debate. I think this is true. And part of their popularity might come from a very good C library that implements them. Because if you've got great research papers and no code, you don't get used. All right. So is everybody following? Has opened up the notebook. So we're going to do the standard imports. The support vector machines, the SVMs, they're found in Scikit-Learn.svms. And I want to start with some intuitions, especially with linear SVMs. So first of all, linear SVMs are really linear models. The reason we did not put them in linear_model is that people are so much looking for SVMs that they expect to see a module called SVM, but they could be there. So we're going to instantiate an SVC, which stands for Support Vector Classifier. So there are two kinds of SVMs, the SVR and the SVC, Support Vector Classifier versus Support Vector Regressor. We're going to start with classification, and we're going to give it kernel equals linear to be working with a linear support vector machine. And then we're going to take our favorite simple data set, which is the iris data set, and take only the two first features to be able to do visualization, and then fit an SVC on this. Easy? Runs? It's got a bunch of parameters. We don't understand what they mean. Not important. And then what we're going to do is that we're going to do something that we already did this morning, which is we're going to plot a prediction on a grid of points just to get an intuition of what it does. So I'm going to run this code, and then we're going to go over it. Okay, so what this code does is it takes an estimator, data, fits the estimator on the data, and then plot the decision of this estimator on a grid of points, right? So you can see the output here. And the way you do it is simply you build a mesh grid that covers the area that you want to cover. So that's X and Y. These are going to be your two features. So then you want to ravel this mesh grid, right? So the X and the Y, here I call them XX and YY. They're 2D arrays. You want to ravel them, concatenate them to have a sample by feature matrix, and then you can do predict on this, right? So then you get the label that's predicted as a function of the position, and then you reshape them back to a 2D array, and you can plot this, right? This is all fairly simple, though a bit tedious NumPy array manipulation. Is that clear for everybody? So we do a lot of this just to get intuitions. Now, one caveat is that these are intuitions in low dimension with only two features. They don't always extend to high dimensions. So you got to work on thinking in 64-dimensional space. Okay, so kernel equals linear gives us linear decision frontiers. If I take two classes, the decision boundary is a line. We've got three classes. How does the decision work? Well, the estimator splits the problem in a set of two class problems. So it does a 1 versus 1. Every pair of class, it learns a decision rule, and then it has a voting heuristic for each pair, right? That's called a 1 versus 1 approach. One caveat is that we have two implementations. Well, we have several implementations of SVCs, but in the SVM module, we have two implementations. One is the SVC, which uses libSVM, and the other one is the linear SVC, which uses liblinear. So linear SVC does only linear kernels, whereas SVC does more. They use different underlying algorithms, so you're going to have different convergence problems, different speed. All gets very technical, but one caveat is that linear SVC uses a 1 versus all strategy, whereas the SVC with kernel equals linear uses a 1 versus 1 strategy. That's because the underlying libraries made different decisions. Important to keep in mind because you're actually changing a lot when you're switching from one to the other. If you want to have control on this, we're not mentioning it here, but there is a meta estimator that can apply 1 versus 1 or 1 versus all given one estimator, okay? Does that make sense? Right. So if we look at a linear SVC and look at the decision boundaries, they're slightly different because it's a 1 versus all strategy. All right, so I'm not going over SVRs, but just think of them as things that work like SVCs, but for regression. So with a linear support vector machine, we know our model class. It's a linear model. So then what we don't know is what kind of regularization we do with this. And I'm going to cover this by talking about support vectors. So I'm going to run this code and discuss it. So what we're doing here is we're just taking the 2-class problem for the 2 first class. Just so we're 2 features, 2 class. That's just about as simple as you can get. And then we're looking at the decision that is learned by the support vector classifier on this problem. And on top of this, we're plotting the support vectors attributes of the SVCs. So it's 2-dimensional n samples by n features, where n samples here is the number of support vectors. So we're plotting it over as an overlay to our training samples. So the way a support vector machine works is that it learns a linear model that is spanned by a small number of training samples. The idea being that it tries to find the training samples that are close to the decision boundary. And that number can be tuned by the C parameter. Okay? So here we use the default, just C equal 1, and we can see that it's used approximately 50% of our training data to learn a decision boundary. And the intuition really is that if we're trying to fit a discriminative model, the samples that lie close to the decision, the sample for which it's hard to make a decision, are probably the ones that are valuable. This may or may not be the right choice depending on the data you have. One nice thing is that it's fairly sensitive to outliers. I mean, I can have something way out here moving around. It's not going to change anything to the decision boundary. So that's the picture to have. Now, choosing the amount of support vectors that we use is, in some sense, a form of regularization. It is the regularization that the SVM has. And this can be tuned using the C parameter. If I put small values for the C parameters, I have a lot of support vectors. And in a sense, if I do this with a very, very small value, my decision frontier is pretty much spanned by the mean of the first class minus the mean of the second class, right? This would be my decision frontier. On the other hand, if I have very high C values, I use a very small number of support vectors. And I'm fully driven by the most discriminant samples. Now, historically, the reason why SVMs were popular is that with very high C values, the algorithm that's used by SVMs can be very fast. It doesn't need to look at a lot of data. At least doesn't need to iterate on a lot of data. So that's another thing that kicks in, is that quite often we see that changing the amount of regularization, changing the meter parameter, will also explore models that have a very different computational cost. We'll see this, but the really nice thing about SVMs is that, in my experience, they're not terribly sensitive to the choice of regularization parameter. And I don't know of any theory that tells us why. It's just my experience. So let's plot the two extremes. So highly regularized and almost not regularized. Highly regularized does not look like it's that regularized. I'm going to crank this up. Right, so a bit better. All right, so you can see the two extremes, and you can see that the decision boundary is fairly different. One thing that I haven't added in the notebook that I should mention is that, so the standard parameterization of the SVMs, which we have here, is a constraint parameterization that cannot be directly linked to the number of support vectors. In general, it's probably a good thing because this parameterization is a bit more independent of your data size and of your signal to noise ratio. But there's another parameterization in which you pretty much set an upper bound on the number of support vector machines. And it's called a new SVM, as in new, the Greek letter. And the new SVM is exposed in the Scikit-Learn. So if you really want to control your number of support vector machines, then the new SVM might be an option. Okay? So as a practical note, like many other learners, not all, but many other, normalizing your data, so having basically equal variance features is fairly important for the SVM. In practice, it makes a lot of difference. So we would advise you to normalize your data. And there is a preprocessor in Scikit-Learn preprocess to do this. I'm not getting a lot of questions. Is lunch going through? All right. Now let's talk about kernels. What really made the SVMs popular is that they can work with a wide range of decision frontiers. We saw this a bit this morning with an interactive demo. And the way you do this is that you set what's called the kernel of the SVM. And if you set the kernel to be, so basically the kernel controls how support vectors, or rather observations, are assembled to build a decision boundary. And if you set it to linear, you're going to have a linear decision frontier. Polynomial, so poly means polynomial, you're going to have polynomial decision frontiers, and then you can tweak the order of this polynomial using the order argument of the SVM. An RBF uses a radial basis function, so basically it means that it's going to stick basically a Gaussian kernel, or a radial basis function, at each support vector, and then build a decision frontier with this. And hopefully the plots will make things clearer. So we've got the linear kernel, we've already seen it. Polynomial kernel, we can see that we have a polynomial and the RBF. So what we can see here is that basically each of these support vectors, so here all the data, have an RBF, so a Gaussian kernel that's sitting on them. And one class is going to have, we can picture this as one class having positive Gaussian kernels and the other ones having negative. And then the decision boundary is where the sum of these things crosses zero, right? So quite clearly, this is kind of a messy decision boundary. We're probably overfitting here. So we can see that linear models are simpler, polynomial models are more complex, and RBF are more complex, right? So what's important is the size of the RBF kernel. Here I've taken a size that's fairly small. If I extend the size, I'm going to get a smoother decision function. And that's probably a good thing. So that is one way of seeing regularization. It's a bit like k-nearest neighbor, where I'm having a large number of k. So actually, if you want intuitions, RBF is somewhat related to k-nearest neighbors, because it uses local neighbors in the feature space to make the decision. And the size of this neighborhood is controlled by the, I believe it's the sigma parameter, no, the gamma parameter of the RBF. And if we put gamma to a somewhat decent value, say the default one, then then what we get is that gamma is really big compared to our separation between samples in this situation. And so you've got Gaussians that are really big, and you have +1 Gaussian, -1 Gaussian. So basically what you can see at this scale is that the decision frontier is linear, okay? And if we put gamma in something that is in the middle, yep, so then we have a smoother decision function that's not a straight line, all right? So if you're going to do SVM RBFs, then you have 2 parameters to tune, one which is C, the other one which is gamma. Should we do the exercise or move on? All right?
What is the, this is a fairly black box. I mean, what's going on in the support vector machine? Is that a bad question to ask? I mean, intuitively, kind of big picture, what are we doing here?
Okay, so the question is, this is a black box. I want to open the black box. I think we've opened the black box quite a lot by looking at the support vectors. I mean, the only answer I can give you is fairly mathy. And I'm not sure we want to go over this. I mean, do you guys want, I mean, because, so the general answer is SVMs, one way of looking at SVMs is looking at them as a problem that is solved in the dual. So instead of parameterizing your coefficients, you're putting weights on your samples. So that's the dual. So as a lot of learning problems, the SVM is a minimization problem. It's got a loss, which is a data fit term. Okay, I mean, yeah, we can develop intuitions. Okay, sure. And people who are not interested in them, they can do the exercise. All right. No, actually, yeah. This is interesting. So you're trying to solve a classification problem. So you're trying to minimize cost, which is basically the error. And the cost that you'd like to minimize is this one, which is I'm counting 1 as 1 error for every training instance that is classified in the wrong class, and 0 for every training instance that is classified in the right class. The problem is this is not a nice function to optimize. It's non-smooth and non-convex. So what we're going to do is replace, so basically you're trying to minimize the sum of this loss function, L, this is L, over our model, so our prediction, and I can x minus f of x and beta, where beta are the parameters I'm learning, for all the training samples. And f can be a linear model if you're using a linear SVM, or it can be something else. If it's a linear model, it's just a dot product of these two guys. Okay? And so because minimizing this guy is really, really nasty, I mean, it's not going to work ever, you're going to replace this by some kind of convex proxy. Okay? And what the SVM does is the convex proxy it takes is the hinge loss. I mean, you got hinge or square and squared hinge, but most often it's hinge loss. So it's this guy. That's the hinge loss. And so what you have is that any sample that is here in this part is not, it's not that it's not used, but it's got a 0 weight in the dual. It's moving it a bit will not change at all the prediction function. Any sample that's here, if you move it, it's going to change the prediction function. And any sample that is here, so these are the samples that are wrongly classified, These are the samples that are rightly classified and far from the border. And these are the samples that are rightly classified but close to the border. So this is the margin. And support vectors lie here. Okay? And if we look, so if we run our SVM GUI, well, yeah, I'm not going to do it. I'm just going to draw something. But basically, if I've got a 2D prediction problem and I've got classes like this, one guy here, one guy here, yeah, I don't know. Okay, and then my margin, my decision rule is going to be like this, and my margin is probably going to be like this. And these guys are going to be the support vectors because one is lying here and the other one is lying here. Okay? And what the C parameter does is pretty much it controls the slope here and therefore controls the size of the margin. Does that make it any less black box? I mean, yeah, support vectors are anything that are close to the decision boundary where close is defined by the margin. That's easier to understand for linear predictors.
For general understanding, we took from the iris data set and ignored two of the features, right? And then we have this certain quality of separation. Do I understand it correct that if we would have run a PCM first and find two good features out of the four and run the SVM on that the separation would have been better?
The question is, what if we had run a PCA to choose our two directions better? Would the separation have been better? The answer is there's absolutely no guarantee. If you think about the example I gave earlier where the variance of the classes is completely not aligned with the separating hyperplane, that will not help. So it really depends on your data. Now, it's just so if you have super high dimensional data acquired on gazillion of sensors and some sensors don't carry any information, chances are the PCA will work well. But don't reduce too much your data set because it's an unsupervised method. All right, let's look at this exercise. Now I have to do it live because I don't have correction. Okay. Okay, so I said that I wanted to tune it, so I'm going to use grid search CV. Okay, so if you remember, the grid search CV takes two things. It takes an estimator and a set of parameters that we want to tune. Well, I'm going to start with linear kernel, just because it's simpler. And then I only have one parameter to tune, which is C. And typically I do log scales. Thanks. And I'm going to go from -3 to 3, and I'm going to take 10 points, and I'm going to run this. Oops. Yeah, missing. And grid dot fit x, y. it's running. So one thing, that was fast. I was about to say that it's slow, not that much. But I mean, what you have to keep in mind is that when you're doing a grid search CV, you're fitting a sizable number of models. So it can be slow. Here it wasn't. So then I can look at the best score, for instance. So that was 0.98. And I can look at the set of best parameters. Best parameters. And it was C equals, wow, it was a very small C. Interesting. So we're using probably a large, sizable fraction of support vectors. So one thing that I can do is look at the scores on the grid. That's a very nasty data structure. It's hard to read because there is no guarantee that our grid is an actual grid. It could be an irregular grid. And if I manage to read this, so it's giving me the parameter, the average score, and the score on each fold. And if I manage to read this, well, actually what I can see is that the prediction did not change at all. Yeah. Okay? So that goes together with my intuition that basically SVMs are fairly insensitive to to setting the C parameter. Okay, so then I can play and I can try something more complex. I can try, so if I really wanted to do this in a clean way, I would try to do training curves, validation curves to see if my model, if I can gain a bit more. But I'm just going to try to do an RBF. I'm going to keep C equals to 1 because it works somewhat well, but I'm going to play with my gamma. And that looks right. Hopefully it's not going to take too much time. And then I can plot this and look at the grid scores. Might take a bit more time. It's a bit more complex to learn. Yeah, it's going to take a wee bit more time. Yeah. Oh yeah, I need to print. So I did improve a bit my model. I went from 98%, 98 something to 99 something. Okay?
And you can see that some gamma values are really bad.
Yeah, and we can see that the gamma matters. If you look at the errors. Yeah. Yeah, quite clearly. I mean, one thing, yeah, that's actually a very good remark. One thing that immediately raises a warning sign here is that my best gamma value is on the side of my range. So, well, maybe I don't have the optimal. So what I'm going to do is I'm going to shift a bit my range and rerun. And hopefully it's not going to take too long. All right, so what I'm doing here is optimizing my meter-by-meter optimization looking at my data. So basically, what you have to keep in mind, okay, so let's see if I can improve things. Well, not really. Okay, so I didn't improve things, so there's a fairly narrow parameter range that improves. So I can tweak it a bit to be there. And what am I doing when I'm doing this? I'm probably overfitting. Remember, an optimization algorithm that tries to minimize the training, to minimize error on some given data, will at some point optimize this so well that if you give it new data, it has overfit. It doesn't matter if this optimization algorithm is a human. So when you start, to try, when you have to move your parameters very slightly to gain a bit on your data, you are overfitting. And ideally, what you'd like to do is to keep some data that you don't look at all until a while, and then you test on it. Okay? Does that make sense?
Just an additional remark. So we can see that for many values of gamma, the mean validation score is 10% accuracy. So this is very, very bad. But remember that we are classifying digits, so we have 10 possibilities. So the random chance level is 10% accuracy in this case. And so for many values of gamma, we are not doing better than chance. So it's very important to cross-validate grid search the gamma value when you're doing SVM with RBF. It's even more important than C.
Yeah, and in theory, C and gamma are related. If I'm optimizing for gamma, I should optimize for C. So I'm not going to do it here because it's going to take a bit more time, but I should really have a great search with two parameters. And one thing, Brian is not there anymore. Jake, so you told me that now IPython works with multiprocessing. So I'm not going to crash everything. Okay, so it works. Well, we can always try. Worst case, I crash it. So many objects have an end job parameter, so end jobs, and that you can put to the number of CPUs that you want to use. And many computers nowadays have multiple CPUs. Okay, yours is 2, so I'm going to put end job equals -1, which means use everything you can. And this uses the multiprocessing module, which is in the standard library. And I don't know if the IPython notebook supports it or not, so we'll see. This gets really interesting when you're setting many parameters on a computer with a lot of, that worked, and it did go faster. So for instance, my desktop has 12 CPUs. My colleague's desktop, they now have 16 or 32. This is clearly an embarrassingly parallel problem. So you clearly have easy parallelism here. All right, I think I'll leave it to chat. Okay. So the question was, is there a reason we're using a grid search as opposed to a simplex or a least square? So the least square, I mean, you have to keep in mind that this is a very, very, very nasty optimization problem, because it is an optimization problem. It's a noisy optimization problem that has absolutely no guarantee to be convex. It doesn't even have the guarantee to have one local minima. So a least square would not work. Simplex I tried. It seemed like a good idea, and it doesn't work. The reason why it doesn't work is that there are parts of your optimization landscape that are flat, except you add noise to it. So simplex completely fails. Now, it is true that you can have better optimization strategy than the grid search. And let's say we're working on them. But they're non-trivial optimization strategy. But things like a HyperOpt, which is a package by James Bergstra, who will be at the conference, uses advanced things like, actually it uses learning strategies on the optimization parameters. It's more complex, but it's definitely worth it.
There is something simple that you can do, and that is smarter than grid search, is randomized search. So you randomize the order of the grid, and you monitor the computation while it's going on. And when you see that it's not improving anymore, you can stop before the end. So it saves this computation, and this is what we're gonna see later in parallel.
Okay, so the next estimator that we're going to talk about a little bit in depth is tree-based estimators. And these have been really, really interesting lately, and actually been shown to be very powerful lately. So we're going to look at the 7.2 notebook, so you can open that up. But basically, decision trees, random forests, gradient-boosted decision trees are all built on a very simple principle of a binary search tree. And it's really nice because if you're thinking about how you as a person would classify something, say out in nature, you see something in the forest and you want to know what it is. first thing you do is, you have something here, and you say, well, is it a plant or is it an animal, right? And then you say, okay, I divided them into plants and animals. And if it's an animal, does it have big teeth or something like that, or is it furry? I mean, that's clearly not the perfect way to determine things. And then, over here you might say, I might run away. And here I might do something else. Yeah, so it's this idea of breaking things down into steps, and at each step saying, what's the most interesting yes-no question I can ask about this thing? And it's kind of where the whole taxonomy of creatures and their Latin names and everything like that developed. So what we're doing is taking that intuition about how you classify things out in the world and codifying it in a machine learning algorithm. So a decision tree is exactly this. It takes the full data set and says, what's the most interesting yes-no question I can ask about it? Divides it into 2 pieces. Then it takes those pieces and repeats and goes down until you have it broken up into pieces that you can easily classify. So very simple concept, and it leads to some very powerful estimators, as we'll see. So one of the reasons decision trees and other estimators like this are so powerful is because they're non-parametric estimators. So before this, a lot of the models that we've been looking at have been parametric models. You fit a polynomial to data. You fit some sort of linear or kernel decision boundary in your classification. Each one of those models has a parameter or a set of parameters that you have to fit. But sometimes you don't know the right parameterization of your data. So here we're going to use a toy data set that's basically a combination of a sine and another sine. So a low frequency sine wave and a high frequency sine wave. So I got to run my PyLab inline. If we run this and then plot the data, this is the data set that we've created right here. So an example of this in real life might be tidal data, right? You know that there's the Earth is rotating and the moon's going around and the sun's going around, and you have some sort of sinusoidal, complicated periodic thing. And the gray line here represents the true values, the inputs, and the black points represent the noisy observed values. So if we knew that this was the sum of 2 sine waves, then we could design a model that could fit for those sine waves, right? But if we don't know that this is a sum of 2 sine waves, and we try something, something like a polynomial regression, it'll take a lot of polynomial terms before we can really fit that sinusoidal pattern. So this is the problem with parametric learners. So you have to parameterize a model, and how well you do fitting your data with that model depends on how well the model is suited to the data to begin with. So I just wanted to show really quickly right here, if you knew to look at this and take, say, the Fourier transform of the data, you could find that there's 2 spikes in the Fourier power which correspond to the 2 frequencies that we're looking at. So if you have the domain knowledge to be able to go in and say, hey, I think this is what my data should look like, and you can explore it with the right tools, you might be able to find a sparse representation. So in this case, you could basically encode everything that's going on with the data set by treating it as a sum of these 2 sine waves. And that's exactly because we generated the data as a sum of 2 sine waves. But you don't always know what that optimal sparse representation is when you're going at a brand new data set. So this is where non-parametric models like decision tree can come in and can be very useful. So the first thing we're going to do with our data, because we're going to be using grid search and things like that, is we're going to randomize our data. And this is an important step that's not built in, but sometimes when you're partitioning data, it can be, so if your data is ordered in some way, then it can mess you up. So we're going to just randomize that right there. Now, the decision tree regressor, it works just like every other estimator that we've seen. You just instantiate it. We're going to say the max depth equals 5. That's basically saying we want to ask 5 levels of questions to go down, and we'll divide our data up into 2 to the 5th different categories with that. Yeah, question? In the case of Scikit-Learn, all our decision trees are binary. I don't think you gain that much by making them non-binary. It makes it computationally, or it makes the code complexity a lot more. And you can also, I mean, you can always go 2 layers to get that sort of thing go.
Yeah, there are other kind of forests like rotation forests where you learn, or functional forests. Yeah, functional forests where you learn more complex splits. So the rotation forest is going to do a PCA, and the functional forest is going to do something like logistic regression. Yeah, it's not implemented in Scikit-Learn.
They're separate decisions, right? The trees don't combine or recombine, right?
The trees don't recombine? So right here, each decision is separate, right? You take a look at this, and then you split the data into 2 pieces, however the algorithm decides that it's best. Yeah, so the branches don't combine back together at all. It's all a tree shape.
Yes.
You can have repeated results at the end. So if you were doing a decision tree on something that had 2 labels, you'd end up with 64 nodes, and some of them would have repeated classes. Okay.
But you probably don't want to go too deep. Are you going to cover this?
Yes.
Yeah.
Yeah. So we're just going to start with max depth of 5 right now because that's a good medium. And the max depth kind of acts as the regularization parameter for decision trees. So as we adjust that, it's as we try to find the best model, that's going to be the main parameter that we're adjusting. So if we do the fit, we compute what the model looks like, and here's all my bad Python install. And this is what the decision tree gives. It kind of gives it gives you a bunch of discrete bins, and essentially each of these bins that you see here on the plot, each of these wide plateaus, is one final bin of the decision tree. We can see that if we change the max depth to say 2. We can see that we only get 4 discrete bins out of the whole tree. So we're doing 2 splits, and 2 times 2, or 2 to the second is 4. So when we do 5 splits, we get 2 to the 5th different bins across the data. Now I've been telling you that decision trees are a powerful algorithm, and looking at this, you might wonder if I've been just lying to you or something. You know, because this doesn't fit very well. It's not hitting the peaks and the valleys, and it's not fitting to the data. We might try increasing the max depth to make it fit better, right? But then at that point, we're just overfitting the data, right? We're just basically finding, it's like a nearest neighbor search, right? At every point, we just compare it to its nearest neighbor and say that's the result. That's what happens if you go to a high max depth. So this is why max depth is similar to regularization. A high max depth is completely unregularized, and a low max depth is very highly regularized. So you get a very, very biased model. So with decision trees, where should you set the max depth? It's got to be somewhere in the middle. You could use a grid search or something along those lines to decide that. But a better way to use decision trees, because they're such a fast classifier, they basically work in log time, and they can be parallelized if you're careful about it. They're fast classifiers, so using a lot of them at the same time is actually the way that people have made a lot of good steps. So the idea is here, if we were to take this result right here, this particular decision tree fits very well in some regions of space and fits not very well in other regions of the space, right? There's some places where it just glosses over the detail and kind of is biased. And there are other places where it almost overfits. It looks at each of the individual points. Now, if we were to take a whole bunch of random decision trees where we tweaked these results just a little bit each time, then on average, some of them would overfit and some of them would underfit in each place. And on average, you might imagine that you'd get actually a better result out from the ensemble than you would from the individual tree. And this is the idea behind bagging or ensemble learning. And it's known probably most famously in the random forest algorithm. So random forest does just this, exactly what I just said. You take the decision tree and you randomize each of these decisions a little bit. So instead of maybe taking the optimal decision at each point, you take some random choice out of the top three splits at each point. And then what you end up with is a tree that by itself is not optimal. And you end up with maybe 1,000 trees that by themselves are not optimal. But combined, they can actually do much better than any single tree by itself. And this is kind of a theme as you go into more complicated learning problems, is that combining estimators, you can actually do better than any estimator by itself. So the random forest regressor is as easy to use as the decision trees in Scikit-Learn. You import it here. You tell it how many trees you want. We want 200. We're still going to do the max depth of 5. We're going to fit, predict, and then plot the results. And this is what we see. So by averaging over 200 different decision trees that are all slightly different, we get a fit that's much better than the fit from a single decision tree. You see that? So it's kind of a cool concept. And one story I heard is that the Netflix prize, this famous contest where people were trying to predict how well folks would like movies based on their viewing history. When that was going on, someone realized that if you took the top 3 or 4 algorithms in the Netflix prize competition and just averaged their results, it turned out that average algorithm did better than any of the top 3 by themselves. So this is this idea. If you randomize things, if you look at specific estimators that slightly differ, you can average them and do much better. Yeah?
Is it the decision that's being randomized or the data that is fed?
Yeah, there are different types of random forests. I believe in this, the question was, are we randomizing the decisions or are we randomizing the data? In this case, I believe we're actually randomizing the decisions, and we're using the full data set each time.
So the default random forest is that you select a subsample of the feature that you will consider to select the best decision split. So you subsample the features, and you can also subsample the samples to do bagging. But the vanilla random forest, you don't do bagging. You just select a random subsample of the features, find the best split on those, and split one level, and iterate this with new random features at each level. And there is also in Scikit-Learn what we call extra trees. They are extremely randomized trees, and they further randomize the position of the split. And it's even better if you have more trees.
Yeah, so the question is there a tree algorithm that does some more complicated regression at each of the leaves? And right now, we don't have that. But I don't know, if you want to do a pull request, we'd be open. Yeah, and you can also there are also bagging type approaches you can do with other estimators besides trees, but I don't think we have those meta estimators implemented quite yet. We have that implemented for boosting, but not bagging. And I'll go into that right now. So boosting is another way to use decision trees, to use multiple trees or multiple estimators in general to do better than a single estimator by itself. And the idea here is that instead of doing everything in parallel, doing multiple estimators in parallel, what you do is you start with a model that really underfits the data, and then you train another model on the residuals, and then you train another model on the residuals of that, and another model on the residuals of that. So you iteratively refine how well your model's doing by applying a whole bunch of models in sequence. And there's some things that go on in the background to make sure you're fitting the right thing at each step. So gradient boosting regressor, that's implemented in Scikit-Learn as well in the ensemble module. And it works just like we saw above, the number of estimators. We're going to choose a max depth of 2 here and fit that and then plot the results. And the gradient boosting estimator looks like this. So essentially, maybe what you can think of what's going on here. Let's say if we do number of estimators equals 1. That's what we get, a not very good fit, right? We're a very, very biased fit. But if we add one more estimator, it gets a little bit better. If we go up to 10, it gets a little bit better. You can see that each time, each estimator we add, we're refining the fit just a little bit more. We're fitting the noise, or not the noise, we're fitting the residuals to do much better. And as we go all the way up to 200, or even beyond, we fit the residuals better and better to the point where we might even overfit the data, right? So these are interesting, and there's one point I want to do here. We have an exercise here, but in interest of time, it's about time for the break. I shouldn't have said that word. I want to just show you the result here. And this isn't. I'm gonna push this to the repository later. I apologize. I didn't do that before. But I just want to do a quick grid search over the decision tree regressor, the gradient boosting regressor, and the random forest regressor. Take a look at the parameters. We're going to look at the max depth from 3 all the way out to 11. We'll grid search to figure out the best max depth, and then we'll print the results, the best parameters and the score. And grid search is not defined. That doesn't help. From Scikit-Learn.grid search, import grid search. Oh, I did grid search dot. There we go. Ah, now it's running. Excellent. So what we find is that looking at this all together, the decision tree regressor doesn't do very well by itself. It's 70% or so. In this case, the gradient boosting regressor only does slightly better, and the random forest regressor is much better. And you could tune these. I set the number of estimators at I think 200 or something. I just use the default number of estimators. I'm not sure what that is. But so you could tune this a little more by setting that. But the interesting thing to look at here is the fact that the random forest regressor needs individual trees that are much more precise. It needs a max depth of 7. And the gradient boosting regressor does better with trees that are less precise, or that are more biased, I should say. So basically, the random forest regressor is taking a model that overfits the data and aggregating a bunch of them together to decrease the overfitting. The gradient boosting regressor is kind of taking a model that underfits the data and aggregating them together to reduce the underfitting. And it's one way that I like to think about these two types of ensemble learners. Any questions? Yeah.
It's a little more time, but that's not usually what you tune when you tune gradient boosting regressors. Usually the depth is left to something small.
Yeah.
Yeah. Step size.
Yeah. Okay. So
usually dominate random forest gradient boosting.
Yeah. So his point is a valid one. When you're looking at gradient boosting, you usually want to tune on the step size, which is basically how much you're refining at each step. And I just did this quickly because I wanted to show you that gradient boosting favors underlying models that are biased, that underfit the data. But, yeah.
Where does the term gradient boosting come from?
That's a great question. What is gradient boosting? Yeah. From the people who came up with it. Yeah, so the idea is you have this, this gradient of residuals, and you're trying to kind of follow your way along the gradient with these individual learners that are underfitting the data. And it's boosting because I guess each time you're boosting your score just a little bit. Is that sufficient? I don't know.
Boosting in general is that you reweight the samples that are causing errors to be more important, so that the next model in the sequence will consider these samples more specifically. Yeah. But for the gradient boosting, it's complicated. You should read the paper.
Yeah. Question?
Different ways of tuning and so on, getting models that have greater or lesser fidelity to the data. None of the models, as far as I can tell, have anything to do with two overlapping sinusoids.
All right.
So, I mean, maybe this is a philosophical thing in machine learning. I mean, you know, at the end of the day, if what I want to do is get physical insight into why does my data look like this in the first place. Is there anywhere to go from here to there?
So this is basically what I do for a living.
Repeat the question.
All right, so the question is, this is a very ad hoc model, and there's no way that we're going to get sinusoids by basically aggregating trees or boosting trees. So if we want to get insight on the data generating process, how do we do? My first answer would be you don't use random forests. I don't use random forests. The other option would be to say, well, you choose your feature space well. If you had a feature space of sinusoids, then it would work. But that means that you already have insight. Random forests are great for prediction. They do give you some insight. I mean, here you look at the sinusoid, it looks like a sinusoid. You also have ways of knowing which features were selected often. So you do get some insight. But you're going to get less insight than a model that has an actual equation that tells you what's the forward model that then you're going to regularize, which is the kind of problems I work with. These problems are not as black boxy. Random forest is really nice, or gradient boosted trees, they're really nice because they're super black boxy. It's harder to inject understanding of your problem.
One more question.
Would you want to do any kind of smoothing with this curve?
Smoothing. The question is, do you want to do any smoothing of this curve? And that curve is kind of an artifact of the way that we've chosen to display this data. It's not that we're particularly trying to fit a spline or anything to our data. It's just that we've represented it that way. Maybe Olivier has a better answer.
It's just that. So one possibility would be, as Gaël said previously, it would be to use another basis for the features, like for instance sigmoids. And if you combine sigmoids using a random forest, you would have a smooth line. But in the real life, you don't fit polynomials for a living. You have high dimensional data, and you don't have this smoothness in your data, especially if the features are very heterogeneous. For instance, if you have a transaction logs with many different values, one is a temperature in degrees, one is a price in dollar and whatever, you don't have any relation like this between the features, and so you don't really care about the smoothness. You are really only interested in the predictive accuracy, and in this case, those kinds of models are really good.
Well, if you're interested in the smoothness, and you're interested in fitting things like this that are called non-parametric models, basically with a number of parameters that can grow infinitely, you should look at Gaussian process regression. That will allow you to set a kernel that basically defines your smoothness.
Okay. I think right now it's time for our break. So it's 5 after right now, so we'll come back around, what time is it? Yeah, we'll come back around 3:20. So see you then.